So let's look at this simulation. In this simulation, there's a light ray that is passing between two mediums. So now let me change the light ray such that it's passing from air to water. Now what is happening here is refraction. Remember that light rays travel at different speeds in different mediums. In this case, the light ray is traveling much faster in air than in water. This is because the refractive index of air is a lot lower than the refractive index of water. Therefore, it travels faster in air than it travels in water. From the activity earlier, remember that as light rays travel from a faster to a slower medium, it changes direction and it refracts. Therefore, we can see that refraction is occurring here. Now what I want you to observe is how the angle of incidence and the angle of refraction is changing. As the light ray is traveling from a medium where it's faster, like air, to a medium where it's slower, like water, the angle of incidence is a lot bigger than the angle of refraction. But when I swap this, what happens is the angle of incidence, like this, is a lot smaller than the angle of refraction. This is because when the light is moving from the water to the air, what is happening is that the light rays are moving a lot slower in the water, then it speeds up as it moves to the air. This causes a reverse effect. So previously the angle of incidence was bigger than the angle of refraction, but now it's the opposite. So the angle of incidence is a lot smaller than the angle of refraction, as we can see here. One more thing I want you to observe is what happens as we increase the angle of incidence. So as we increase the angle of incidence, the angle of refraction also increases, and it increases proportionally. So when I increase the angle of incidence by some value, the angle of refraction also increases by that value. Now I'm going to demonstrate another principle that I will explore later with y'all. So as I increase the angle of incidence in a material with a higher refractive index, the angle of refraction changes by much more. So when I increase the angle of incidence by a little, the angle of refraction changes a lot because the angle of refraction is much bigger than the angle of incidence. So when I keep moving it, the angle of refraction will eventually reach 90 degrees. So what will happen over here? Actually, what will happen is something that's called total internal reflection. So the light cannot refract anymore, and everything will remain internally in this medium. And I will look at this later with all of you. But before that, what we need to remember is that when light rays are passing from a material with a lower refractive index to a material with a high refractive index, the light rays will, the angle of incidence of the light ray will be a lot bigger than the angle of refraction. But when it is the other way around, when it's passing from material of a when it's passing from material of a higher refractive index to a lower refractive index, the angle of incidence is much smaller than the angle of refraction. So we can see this using this protractor over here. In this case, the light ray is passing from water to air. So in water, it's traveling a lot slower. Therefore, the angle of refraction will be a lot bigger than the angle of incidence. So we can see that the angle of incidence is at 30 degrees over here, is slightly less than 30 degrees, and it's at 25 degrees. But the angle of refraction is it's a lot big, it's somewhat bigger than 25 degrees at 27 degrees. This effect increases as we move the light ray bigger. So now the angle of incidence is at 45 degrees, but the angle of refraction is much bigger, and it's at 70 degrees. Now what we can see here is that the angle of refraction is definitely bigger than the angle of incidence. And this is the opposite case when the mediums are swapped.